All right, I know what you're thinking. What about interactions between like particles in the nucleus? In other words, can protons interact with other protons? Can neutrons interact with other neutrons? And if so, what kind of particle do they exchange? Well, a pi zero is a particle with no net charge. So pi zero then is the one that you would want if you were trying to exchange, say, a particle between a proton and a proton, and you didn't want to change the charge or the nucleon state for the system. Okay, and so to make a pi zero particle, you basically need equal amounts of up and anti-up and down and anti-down, as well as equal combinations of the color and the anti-color. And so the actual composition of a pi zero is a little more complex than for a pi plus or a pi minus, just because there are different possibilities of ways to make something that has zero total charge in terms of a quark and its anti-quark partner. But the net result of this, if you've got equal amounts of quarks and anti-quarks of the same type in your pi zero, then you're not going to change the quark balance of either of the particles. And so this can produce an attractive force between protons. We know that electrostatically they're going to want to repel. But this pi zero particle being exchanged between them doesn't change the quark configuration or the charge. So it doesn't change anything about the particle, but it helps to bind it together. And similarly for a neutron, that would be the kind of particle that would be virtual, that would be exchanged in that kind of a situation. Okay, so now next, what I wanted to do is look at some conservation numbers which tell us more about the possible kinds of reactions that can occur. Okay, so we've got two main conservation laws that I wanted to explore here. We have conservation of baryon number and conservation of lepton number. Okay, so we define then for a certain particle its baryon number B and its lepton number L. Okay, so let's just do this for a few normal particles that are first generation. Okay, so this is just still first generation because I don't want to get too complicated yet. But then I'll expand this to individual conservation numbers for the other two generations as well. All right, so let's say that we've got here a proton. That's going to have a baryon number of +1 and a lepton number of 0. Because it's a baryon, it's a positive matter baryon rather than an antimatter baryon. Okay, and so that gives it a +1, so it's our proton. Antiproton will have a baryon number of -1. Okay, so antimatter gets the opposite sign on the baryon number. Similarly for a neutron, has a baryon number of +1. An antineutron has a baryon number of -1. but lepton numbers for all of these are 0. Okay. Now what about for leptons? Let's have an electron. I'll have a baryon number of 0, lepton number of +1. Positron is an anti-electron, a baryon number of 0, lepton number of -1. A neutrino is a kind of a ghostly particle, but it is in the lepton family. Okay, so it has a baryon number of 0, lepton number of +1. So it's in the same particle type as a electron. So it's kind of like how proton and neutron are in the same particle class. They're positive matter baryons. These are positive matter leptons. Okay? And then an antineutrino would be an antimatter neutrino. Would have a baryon number of 0 and a lepton number of -1. Now, these neutrinos, I should talk just a little bit about these neutrinos before we go on. I haven't said much about them so far, but it was discovered more than 50 years ago that in free space, we get a neutron decay. Neutron in about 15 minutes half-life. If it's a free neutron. Now if it's in the nucleus, this isn't going to happen. It's going to stay stable for a much longer period of time because it's constantly interacting by all these other forces that help to stabilize it. But if it's out there in free space, it'll decay into a proton plus an electron. And so what they started doing is they started measuring the energies. And they knew that the electron should be getting most of the energy from the neutron decay. And they were finding that the electron didn't have enough energy to satisfy the principles of conservation of energy with the binding energies as they were. And so it was speculated then that there was another particle, and it was called an antineutrino. Okay, now they didn't know at the time that it was an antimatter version of the neutrino. They just knew it was some ghostly particle, and they didn't, because it was associated with the neutron decay, they gave it the name neutrino. Okay, and then they started searching for it. The problem, though, with neutrinos and being able to find them, this is an antineutrino because it's got the line over it, is that these neutrinos have almost no mass and travel at near the speed of light. I say almost no mass because they do have mass. If they didn't have mass at all, they would automatically go the speed of light. You can't stop a particle that has no mass. You go, hey, slow down. No, it's going the speed of light, whether you like it or not. So neutrinos have almost no mass, which means they travel close to the speed of light. And there's very little interaction. They don't interact much. You can send a neutrino through light years of lead before it will randomly interact with one of the molecules. So very little interaction. So how the heck do you find these things? Well, you allow for a lot of possibilities for neutrinos interacting with things. And so it turns out that they're able to set up this thing which was way below the surface of the Earth because you wanted to get rid of all other radiation that could interfere with the experiment. And neutrinos can pass right through the Earth without even slowing down. As a matter of fact, there's so many neutrinos that there's something like 10 to the 9 neutrinos for every particle in the universe. Every other particle in the universe. So this is by far the most numerous particle in the universe. There's 1 billion times more of these than there are, if you add up all the rest of the particles combined, there's still 1 billion times more neutrinos than all the rest of the particles put together. Okay? And so we've got maybe 1 billion of these things going through our bodies every second, and we don't even notice it. And very few of them would ever, even in our whole lifetime, have an interaction. But they're able to set something up hundreds of feet deep with cleaning fluid beneath the surface of the Earth, so that only neutrinos would be interacting with this cleaning fluid, and then they looked for indirect evidence of an interaction from particle tracks that were given off from the interaction of neutrinos with this cleaning fluid, and they found it. And as a matter of fact, one of my professors at UC Irvine got a Nobel Prize for helping to find the first neutrinos in this kind of an experiment. So this was a big deal. And it turned out that as scientists started looking more and more at the relationship between electrons and neutrinos, they found that they were indeed both part of the lepton family. Okay? And so we will talk more about neutrinos in different applications as we go. But let's go back to this list of baryon and lepton numbers. And so we see then that a regular neutrino would have a lepton number of +1, would be paired up with an electron, and the positron would be an antimatter lepton, and an antineutrino would be an antimatter lepton. And so if we want to conserve baryon and lepton number in this reaction that we just went through here, let's just see if we can do it. See if this is, in fact, a reaction that conserves both baryon and lepton. Well, here's our baryon number, go all the way through. And so for a neutron, that's +1. You can check that out there, sure enough, +1. Proton, +1. Electron, 0. Antineutrino, 0. So 1 equals 1. Okay, so we haven't changed baryon number going from the initial state of the system to the final state of the system. And so therefore, that quantity is conserved because it hasn't changed. Similarly for lepton number, the neutron has a lepton number of 0. The proton has a lepton number of 0. The electron has a lepton number of +1. And this is how we knew it had to be an antineutrino, because we have to have conservation of lepton number too. And so that would be -1. So we get 0 equals 0. So we've conserved both baryon and lepton number in this interaction, and we've identified that this, in fact, here was must have been an antineutrino and not a regular positive matter neutrino. Okay, so now if we can look up at the data projector, I wanted to go to the other generations. Okay, so we've got 3 generations of matter, and nobody yet has a convincing explanation for why there are 3. Why there's only 3 or why there's more than 1, either way. And so in the first generation, we have up quark, and down quark, okay, for the quarks. and we have electron and neutrino. Okay, so these are the quarks, and these are the leptons. That's in generation 1. And generation 2, well, we've got that corresponds to the up quark is the charmed quark. Okay, so that has still a charge, you'll notice there, of plus 2/3, just like the up quark does. The equivalent of the down quark is a strange quark. And so these have a charge then of minus 1/3 plus 2/3. And then for the generation 2 lepton, we've got the mu meson and the muon neutrino. Okay, so it means that a mu meson has a different kind of neutrino associated with it than a first generation lepton would have, which would just be an electron neutrino, which we could just put a little E here to indicate that there's more than one type of neutrino. And then for generation 3, we've got the top quark has a charge of plus 2/3, and the bottom quark has a charge of minus 1/3. And so what happens as we go up in generation here is that the mass increases, but charge and spin stay the same. So it takes more energy to make, say, a charmed or strange quark, or a top or a bottom quark. And then for the lepton, we have a tau meson and a tau neutrino. This is a mu meson. Now remember, we talked about mu mesons before and how they will tend to decay. In special relativity, remember when they were produced in the upper atmosphere? We said that they were being produced by solar radiation in the upper atmosphere. And so what was that doing? Well, basically it was a piece of solar radiation would hit an electron and it would give it enough energy, mass energy equivalent, to create a mu meson out of it. Okay, so it would kick it up one generation to the mu meson. Okay, and so in terms of baryon number and lepton number, this would have a lepton tau number of plus 1 for these two. This would have a lepton mu meson number of plus 1. Whereas the anti-versions of these would have a lepton number of minus 1. And then here we have the lepton electron number would be plus 1 here. Okay, and so individually then we have to conserve lepton number through each generation. Okay, so it's not as simple as just having a single generation conservation number. And so we should then say here that the tau plus would have a lepton number of minus 1, and the anti-tau neutrino would have a lepton tau number of minus 1. And then similarly here, the positive mu meson and the antimatter mu neutrino would have a lepton mu number of minus 1. And then similarly here, the positron and the antimatter electron neutrino would have an L electron number of minus 1. And then similarly here, the charmed and the strange quark this would have a generation 2 baryon number that would be equal to +1, but a baryon generation 1 number of 0. So the baryon lepton number for generation 1 would just be +1. And then similarly for the anti up and the down, that would be actually here we have to combine these into baryons before we can do a conservation baryon number for these. So let's just leave that as it is. Sorry about that. Okay, so let's go on to the next example. And in our next example, let's take a look at a multidimensional conservation of lepton number that is basically the decay of a mu meson. This is what we talked about before. Remember that this is what takes 2.2 millionths of a second, is the mu meson will decay into an electron plus a mu meson neutrino plus an antimatter electron neutrino. Okay, and so let's conserve LE numbers here. Okay, for LE, this is a mu meson, so it's second generation, so it has an LE number of 0. But LE for the electron is +1, and the mu meson has a LE number of 0 because it's second generation, it's not first generation. And the electron neutrino has a LE number of -1. So we have 0 equals 0. Let's try to conserve L mu as well. L mu here is going to be +1. This is going to be 0 because this has got a lepton electron number of +1, but a mu, it's not a second generation, so its lepton number is 0. And then our mu meson has a L mu number of +1, and the antineutrino has a number of 0. So we get then 1 equals 1. So this is one of the guiding principles then that allows for us to look at what's going on with particles that are moving from one generation to another, and which of these interactions is going to be possible for that kind of a process.